Good afternoon, I am Mr. Ish. You are joining me for a good video over here. The title over here is very well written out in the sense that the title being some type 1 improper integrals behave very appropriately. What are we looking at here in terms of improper integrals of type 1? Well, we've done a few videos and we know now what type 1 integrals are. They're the ones with the infinite limits. And what are some of these improper integrals that behave very appropriately in the sense that you will have a very clear finite area determination and they will very well and easily display convergence. That is, the integrals are convergent. And what are these forms? We're looking here at this exponential. If you were to do some integration with regards to this and make it an improper integral, you'll find out that they'll behave quite contrary to an improper integral. I want to present 4 examples over here in terms of them being worked out, but very quickly, and I promise you this will be worth your time. We'll start with this very first example and then we'll go through 4 in total. We're looking here at this very first one from minus infinity up to 1. We're looking at e to the x dx. We know what the graph of exponential is. Think about it. It's coming here from minus infinity going to this 0, 1 y-intercept and towards the direction of positive infinity. We're looking here at what? From minus infinity all the way up to this 1 right here. So we're looking at all of this and then all of this shaded area. We have to find the area of this. And how can we do that? And we will do that in this. We will get directly to this procedure because I presented several videos and we know how to do this. Limit as t approaches minus infinity, everything becomes written as this. And this integral is so beautiful in the sense that it's very easy. The antiderivative is very easy. E to the x, the antiderivative from 1 to t, limit as t approaches minus infinity. What do we get over here? Upper limit 1, lower limit t, which is minus infinity, feeding in the difference of the two to give us what we are looking for. We'll do e to the 1 minus e to the t. And we know limit as t approaches minus infinity. We're really looking at e to the 1 minus e to the minus infinity, which is e to the 1 minus 1 over e to the infinity. A number so large here in the denominator that this will zero out and your answer will be just e to the 1, or you can just say right here e. E to the 1 is e. And we have a very clear finite answer, and here we see a convergence. So what is indeed a true type 1 improper integral behaves very appropriately. The second example will go through a good similar routine as the first one. Let's start with the graph. We have e to the minus x. It's basically e to the x but reflected across the y-axis, and the graph would look something like that. A reflection across the y-axis. You know the limit here is from minus 1, lower limit going all the way up to infinity. We're looking at everything over here in terms of its graph. Right after we do this question, we'll do a little bit of quick talk on this whole convergence of this specific and the previous example, and we'll show you and explain why these are behaving very well. E to the minus x, we have to do the antiderivative of that. Before we do that, we'll set the limit. Limit as t approaches infinity, we're looking at minus 1 to t e to the minus x dx. You know the integral of a function such as this is always, when you integrate e to the ax dx, it becomes e to the ax over a. Over here, I have an a value and that a value is a minus 1. So we'll have to bring that in. When we do the antiderivative, we're getting basically this. We're getting e to the minus x over minus 1 from an upper limit of t and a lower limit of minus 1. Here we can write limit as t approaches infinity. We should probably put that down so we don't miss out on too much here in terms of proper terminology. And that's what we have. This minus can be brought outside. Minus 1. Then we can say limit as t approaches infinity. We are looking at e to the minus x from upper limit t to minus 1. Now let's plug in the limit. We'll put a minus 1 out here. When we have e to the minus x where t is coming in and then minus 1 coming in, upper and lower limit, the difference of the two, we'll have e to the minus infinity over here. And then we'll have minus e to the minus 1. You have to work this all out. This is no different than 1 over e to the infinity, and this right here is no different than e to the 1. So you're looking at minus, this zeroes out right here, 1 over e to the infinity zeroes out because it's such a large denominator, and 1 over that, it zeroes out. You have minus e to the 1, and that gives you e to the 1, positive e to the 1. You can see that minus and this minus cancel out. So you have a very good finite answer here, which is represented by the word convergent, that this integral is convergent, and you're seeing convergence. We are breaking away for just a minute or two and looking at this quick prelude to the ending which will come, and a good finality it will be. We've looked at this exponential and that reflection of that exponential across the y-axis. We've looked here over the interval minus infinity to 1, including 1, and the same reflection of that exponential from minus 1 including minus 1 up to infinity, and we've seen in both cases the area for both of these has been a good solid finite number e in both cases, and we've seen that's a good convergence in terms of a value, a finite area representation, the area below the curve, and the fact that a limit exists is very well corroborated by coming at a good finite value of that area. But why is these two particular cases working out the way they are? We have to look here at these diagrams I've drawn for you, and you see here I'm looking at this one, exponential function minus infinity to 1, and then likewise here minus 1 to infinity for that e to the minus x. But let's focus right here. We are saying from minus infinity all the way up to 1 including 1 the area is e. So there, in my mind, there should be a good proportion of this area coming just from 0 to 1. A large proportion of this area is coming from here, which means a good minute but finite amount is coming from minus infinity to 0. Likewise, if we focus here, we're getting a good proportion of this e area coming into here from this part of the interval alone, meaning that from 0 to infinity we're getting a minute but a good finite amount from that. But what exactly is this amount coming from just minus infinity to 0 and right here from 0 to infinity? Well, that remains to be seen, and once we can determine what this finite minute amount of fraction is, and you'll be pleasantly surprised to see what this is, and that is what we're looking at next. But once we figure out this part right here, we'll know exactly why the convergence is playing very well in these cases of this function right here and this over here, and why we're seeing a good representation here of an improper integral behaving very much like a proper integral. So the finality is coming next with a re-examination of both of these functions here, but looking here only at this interval, minus infinity to 0 for this, and then 0 to infinity for that, and it'll give us a good representation of this minute but finite area that develops. These last two examples that I'll present will be defining in the sense that they'll bring the topic and the theme of this specific video to home. You'll see exactly how and why this is the case when we go through these. We're looking here at e to the x 0 to minus infinity, or you can say minus infinity to 0. This right here is e to the x. We're looking at all of this portion going from 0 all the way up to minus infinity. You would expect it might be like infinite area, but it won't be. It'll be a good small finite number, and we'll see true convergence come into play. We're looking here at limit as t approaches minus infinity. We have 0 t e to the x dx. You know its antiderivative is this, and limit as t approaches minus infinity, we have to plug the upper and the lower limit in. When we plug the upper limit, it's just e to the 0. When you plug the lower limit, it's e to the minus infinity, which you know you can write without that negative exponent, and you can write that as 1 over e to the infinity. 1 over e to the infinity is no different than you saying 0. So all of this in terms of the area below the curve from minus infinity to 0 comes out as e to the 0, which is just 1. And there it is. You're seeing true convergence come into play and a true improper integral behaving very appropriately. All of this area from minus infinity to 0 will always equal 1. Let's look at this case over here. We have e to the minus x. You know you're looking at something like this. All of this from 0 up to infinity. You'll do limit as t approaches infinity. We are looking at from 0 to e to the minus x dx. I've already shown you the antiderivative of this. It'll be e to the minus x over minus 1, right? But I'm going to write this in a more better way. I'll do a minus 1 and then limit as t approaches infinity. We have the antiderivative already established here, e to the minus x. I've just brought the minus 1 out. We're looking at it from t to 0. You'll have this minus sitting out. Let's do the upper and the lower limit. E to the minus infinity, because t is in infinity, minus e to the minus 0. Minus 0 is no different than you just saying e to the 0. Minus positive 0 or just 0. E to the minus infinity is just 1 over e to the infinity. This will 0 out. You're looking at minus e to the 0, which is just going to be positive e to the 0, which will just be positive 1. So this area right here, a finite area of this entire portion, area over here is always equal to 1 from 0 to infinity for this function here. Likewise from minus infinity to 0 for this function here, this area below the curve is always 1. So these are two defining examples over here, improper integrals in the sense that there's an infinite interval involved, but you see a very good convergence, a very good finite area that develops all of this. It's finite, there's convergence, and it's done. And with that, I bid you all a farewell. Thank you for watching this video. Hopefully it is meaningful to you all. Thank you for watching. Have a nice day.